Hey everybody, let's debrief some highlights from the classwork problems. So the goal of this first problem was just to understand what's the effect when you replace the distance with its own opposite. So like here we've got a bunch of points at distances. Here we've got the same angles but negative distances. So if I'm at an angle of 0 and I go distance 2, that's here. Angle pi over 4, distance 3 would be, let's try and sketch this. Oops. Whoop. Would be approximately here. For C, pi over 2, distance 4 would be 2, 3, 4 up here. So let's just do that many, okay? So ABC. What happens when we go the opposite distance? So if I'm at an angle 0 and I go negative 2, that takes me here. So here's A. Here, pi over 4, I go the opposite distance of 3. That takes me approximately here, would be B. And then facing up, if I go the opposite direction to negative 4, that takes me here to C. So you'll notice that, I mean, if we want to connect them, we could. I didn't really say to, but you could imagine that. So what you'll notice is that there's a sort of a symmetry here. So think about how you would think about the effect of replacing the distance with the opposite distance. When we're in rectangular coordinates, if I replace x with opposite x, that would be like a horizontal transformation. It's a horizontal reflection. If I replace y with negative y, that would be like a vertical reflection. So if we want to think about this as a reflection, how is it really reflecting? Well, A looks like it's reflecting horizontally. C looks like it's reflecting vertically. B looks like it's reflecting kind of diagonally. But what they all have in common is they're reflecting across the origin. So I think a great way of thinking about this is as a reflection across the origin. All right, for part 2, there's one big takeaway, which is this. For rectangular coordinates, if I have a point in space, there is exactly one set of coordinates that describes that point. Here it would be 4, negative 3. And there's no other set of rectangular coordinates that describes this point unless you have a number that's equivalent to these numbers. So for example, I could do like 6 over 2, but that's just equivalent to 3. That is not true for polar coordinates. For polar coordinates, this point at 3 pi over 4 was this point B right here. I could get that same point if I went an entire 2 pi, if I traversed an entire angle of 2 pi again. So if this is pi over 4, and then I went another 2 pi, that would be 9 pi over 4. So this you could describe as 3 pi over 4. You could also describe it as 3 9 pi over 4, and it's the exact same point in space. Because a negative distance you would plot in the opposite direction of the angle that you're facing, we can also get to this same point if we're facing, this would be an angle of 5 pi over 4. Let's count it up. 1, 2, 3, 4, 5. So 5 pi over 4 with a negative distance. So this point B is also described as negative 3 5 pi over 4. So there's lots of different equivalent polar coordinates that describe a point in space, and that's a big difference from rectangular. All right, so let's start getting into some of the more interesting shapes and practicing how you make sense of them. So here's a graph of y equals sine x. Here's a graph of r equals sine theta, and it's a little small here, but you can see it larger here. Something that you might notice is that this is the x-axis. So sine theta, when you plot it in a polar setting, makes an entire circle, but it's an entire circle that's centered at 0.5, and it's above the axis. So why is that? A great way to start making sense of polar equations is the same way that we plotted them in the first place. So let's imagine a couple of different points and think about where they plot, and then imagine kind of how would you fill in the middle bits. So point A here is at angle 0, facing to the right, distance 0. So this is point A. Point B is facing up, and it's at a distance of 1. So here we are at point B. How did we get from point A to point B? Maybe let's fill this one in the middle here. So at an angle of pi over 4, let me get a pencil. An angle of pi over 4 is that angle. What's the distance? Well, we actually know what the sine of pi over 4 is. It's a height of root 2 over 2. So what's the distance of root 2 over 2? Well, one thing I'd like to point out here, if I kind of extend this out a little bit, this is 1. This is supposed to go through there. So since this is a diagonal line, it should take us from 0, 0 up to 1, 1. What is this whole distance? This whole distance, if we use the Pythagorean theorem, is 1 squared plus 1 squared, so that's 2. And then I take the square root of it. So this whole distance is root 2. So root 2 over 2 should be half that distance, and so it should be right here. So putting it together, this point right here, which I will call alpha, I'm at an angle of 45 degrees, and I've gone a distance of root 2 over 2, and that takes me exactly to this point. So that's why, and you could continue to subdivide and fill in other points, but that's why it makes sense that as the angle increases, let's draw a couple angles here. So as the angle is increasing, the radiuses, the radii, are also increasing to sketch out this kind of half circle. Okay, so where are we so far? We've gone just this first quadrant from angle 0 to angle pi over 2. The second quadrant is just symmetric, so it's taking us from a distance of 1, and the heights are going back down to be a distance of 0. And so that's what's sketching the other half of the circle. Okay, so far we've got that this part of the sine curve has now created the full circle there. So what's this part of the sine curve doing? Let's imagine it. Let's start with point D. So if I'm at an angle of 3 pi over 2, I'm facing downwards. But I'm going to travel a distance of negative 1. So if I'm facing down and I go a distance of negative 1, that takes me in the opposite direction. So D is right back up here. It's at the same place that B was. And so that's a clue about why we're not actually plotting anything down here. When my angles were from 0 to pi, so all of these pencil angles, this direction, I'm always going a positive distance, and so it's plotting part of my circle up here. When all of my angles are between pi and 2 pi, so all these pink angles down here, I'm not going positive distances to plot down here. I'm going negative distances. So when my angle faces this way, I go the opposite way to plot. When my angle faces this way, I go the opposite way to plot. So all these angles are plotting the exact same set of points up here. So this part of the arc traces one circle. This part of the arc traces the exact same circle again, but with the negative distances. I think it's very instructive to watch it happen in Desmos. So let's watch it happen in Desmos. All right, here we go. So far, because you can tell this line shows me the angle. So the angle went from 0 all the way to pi, and I've traced a full circle. Now we're about to trace the second part of that sine curve as the angles are facing down. And you can see the point is redrawing the same circle. So again, let's think about it. When my angle is facing down this way, the radius is the opposite direction. When my angle is facing down this way, my radius is in the opposite direction. So it's the same distance it would have been, but now up here. To check your understanding, so we just figured out why does y equals sine x end up looking like a circle above the axis. What if we were going to do opposite sine x? Or what if we were going to do absolute value sine x? So we could think about what effect that would have on the rectangular equation. This is like a vertical reflection. So here it would look like this. Wow. Let's just pretend that I'm graphing these well. This would be an absolute value, so whatever negative y values I had in the original would now become positive. So that would be more like this. So decide, what would these curves look like as polar? Pause the video, think about it for a minute. So here would be point A. Point B is at an angle facing up, but the distance is -1. So B actually plots down there. C is pointed left, but it's at an angle of 0. D is pointed down, but it's at, it's at a +1 distance. So the angle points down, and I actually do go down. So this is also D. So this seems to be the same story all over again that drew this one, only now it's below the axis. And that's right. Don't be fooled and think, oh, the negative sign reflected this vertically, and this one is also reflected vertically. That's true about this example, but remember what we said before. A good way of thinking about this would be all of the points reflected through the origin. So this point reflected through the origin down, thinking about it, here. This point reflected through the origin down here. This point reflected through the origin down here. So when all these points reflect through the origin, they end up down there below the axis. Okay, what about this one? So do the same thing. A, B, C, D, E. This first half of the graph, here's A. When I'm at an angle facing up, my distance is 1. When I'm at an angle facing left, my distance is 0. So that, and I mean actually this part is identical to this part up here. Those were the same, and so we would expect, because this one traced a circle, that one also traces a circle. So this is the only different part. For all of these angles, I'm facing down. Remember my pink angles from before? So now that all my pink angles are facing down, all my distances are positive this time. So if I'm facing down, last time it was a negative distance, and so I plotted the opposite direction, so it just did that same circle again. Here I'm facing down, and I'm actually moving down, and so this is going to create a second circle right underneath. And so it would create this sort of shape. All right, next time we'll start thinking about more interesting families. I hope that you're starting to get a feel for thinking in a polar way.